In the previous demo, we witnessed the training, classification, retraining, reclassification cycle. In this example, the classification was perfected and the entire image set was classified. Here is a thumbnail view of the scanned tissue. This is a different lymph node, also from a breast cancer patient, this time imaged at 40x. It is immunohistochemically stained for A1A3, red for breast cancer, CD3DAB brown for T cells, and of course counterstained blue for all nuclei. Here's an example of the native resolution of the subimages. Here's the phenotype retraining panel. Many phenotypes are sought after. Here's the familiar CANC-N, the cancer nuclei, again colored neon green. We also have immune, which are the CD3 positive nuclei, colored yellow. And we have BAC-G, which are the other unstained nuclei, colored cyan. In addition, we have CANC-M, the cancer membrane, colored white. Notice that the center's checkbox is left unselected. GemIdent did not attempt to locate the centroids of the cancer membrane. This would be a tough question to answer, as the membrane appears to be joined in large blobs that span many images. You may have also noticed that the identified mask looks a bit like a checkerboard. Every other pixel was left out of the classification. Hence, the pixel skip was 1. Note that there are many training images, probably from multiple cycles of classification training. Also note that we have the ability to boost on any image in the scan, since they were all classified. Now, let's begin some data analysis to demonstrate GemIdent's powerful features. We will first build the global results from the individual classification files. For each subimage in the image set, GemIdent recorded the locations of all 4 phenotypes in a binary matrix. For instance, for cancer nuclei, a resulting image will be solid black with a white dot for each centroid of a cancer nucleus. The build function will take all these resulting images and place each in its appropriate location in the context of the global image. How much memory are the newly built images using? About 100 megabytes. GemIdent stores these humongous images in a proprietary format that takes only 1 bit per pixel. Let's see how big they are. That's pretty large. I wonder what the counts are for each phenotype. So we have about 6,000 cancer cells, about 9,000 immune cells, and about 11,000 cells, other cells which we haven't even stained for. Let's save them to the hard disk. Although we have trained long and hard, there may be some lurking false positives. There's a built-in correction function. GemIdent has segmented the global image into 3 pieces, and we will correct the first one shortly. In the meanwhile, let's take a look at some of the functions available for data analysis. All the functions are listed and documented by typing help. The basic operation of displaying, saving, and loading, and also deleting are here. We've already seen size and count. We also have scaling. We'll look at the result of that later. Then we have the standard binary image manipulation, such as dilate and erode. We also have combine using non-exclusive OR. Then we have the analysis functions, which we'll get to momentarily. Let's load the correction image. We can see the fully identified image at full resolution. Let's try to find some false positives and eliminate them. Here's a couple. Deletions here will be reflected in the global image. For the most accurate analysis, the entire global image must be checked. It may also be interesting to inspect the cancer membrane to investigate cancer structure. I've already scaled the CanSem matrix to something reasonable to view. Notice how trying to display the original image will give an error because we've reached the maximum image size. Here it is. Notice the large and small blobs. It may be interesting to count the number of blobs and get an idea of their locations and size. The label function would do just that. We need to define a minimum size. I'll assume for the moment that a typical cancer cell has a radius of 10 microns. Therefore, the size would be about 310 microns squared. Now let's let this run. Notice that the analysis page is fully parallelized. There is no limit to the number of commands that can be executed simultaneously, and all available CPU cores will be used. Compare this to other languages such as R and MATLAB, which take single commands in series and only use one processor. The labeling is now done. We have about 300 blobs of 310 microns squared or greater. Here are the sizes and centers of them. Now, it may be interesting to investigate how close one cell population is to another. Let's see how many immune cells are within 50 microns of a metastasis. We'll use the num within radius function. How about the number between 50 and 100 microns away? We'll use the num within ring function. Here are the results. There were a lot of immune cells close to cancer, and there's also a lot of immune cells that are within a fair distance from cancer. The general question may be to ask, what is the distribution in general? That is, somehow illustrate the distance from every T cell to the closest cancer nucleus and display the results as a histogram. We'll use the distance away distribution function. This illustrates that most are within 100 microns from cancer. Now, if the same analysis is to be done across many scans, it doesn't make sense to type the same commands many times. Luckily, there's a scripting function. I created a script with analyses I'd like to see performed. The script can be executed by using the script menu and selecting the file. At the end of the script, it displays all tasks joined. If you need one task to execute strictly before another, The join command will force all previously executing tasks to complete before accepting new ones. Now, at the end of the analysis, it may be convenient to have output that you can email or show at a presentation. The report feature will do just that. The auto-generated PDF includes a thumbnail, as well as a transcript of the analyses and their results. I hope you got a glimpse of the power of GemIdent technology in these 3 demos. The development is still in its infancy. Support for more automated microscopy systems and new analysis functions will be added in the near future.